Ladies and gentlemen, this class recording has started. So anything that you say possibly can be used against you because it'll be, remembered forever on the internet. So again, if you don't want your mom to hear this, then don't say anything dumb, and then we won't have to worry about it. Okay? So yesterday, we continued our discussion about Schrodinger's model of the atom, which we sometimes refer to as the quantum mechanical model. And this picture here, oh, not that picture. This picture here showed our progression of our atomic model, starting with Dalton and then all the way through Schrodinger. So, give me some features of Schrodinger's quantum mechanical model of the atom. What did Schrodinger say about the structure of an atom? Jason, go ahead.
Where it is at any point.
You can't tell where what is at any point. The electrons, right? There are areas where there are higher probabilities of finding electrons, but the possibility exists that electrons could be anywhere surrounding the nucleus. We took that idea yesterday and we started quantifying it a little bit more. These areas of high probability, areas where we are likely to find electrons, we gave a name yesterday. Do we remember what we call them? You can look on the front page of your outline if you can't remember because we wrote it down yesterday. Rachel, go ahead. Orbitals, right? Bohr has orbits, right? Really defined places where electrons are. Schrodinger's model is more of an orbital. It's a general area where there might be electrons, or there probably is electrons, but there is no definition in here, right? It's not an exact location, it's just areas of probability. Okay? Good there. All right. So yesterday, we started drawing this picture. Okay? Now, after class yesterday, I went through and I did a couple of things, so my picture is going to be a little bit neater, but the ideas are still there. Okay? So, first thing we drew was this, right? This little yellow sphere. And we said it's real close to the nucleus. This is our first orbital. Okay? Very close to the nucleus. What could we say about electrons that show up in that orbital? Dublin. They have pretty low energy, right? And that makes this prime real estate, right? This is where electrons want to be. But we also introduced the idea that while this is a space of high energy, low energy, my bad, okay, because it's close to the nucleus, if we start putting too many electrons in that space, what starts happening? Nora? They start repelling, and that's not good. That's a high energy situation, okay? So, while this area is a low energy situation, we can't fit a whole lot of electrons there. So, we move it out, right? So it looks, anyway, hold on a second. Thought I had this in order. I'm going to be mad if I don't. Oh. All right. So, next thing we added was this red sphere, and I got rid of the yellow sphere inside of it. Sorry, I went in the wrong order. I apologize. I did all this work and then I messed up. Forgive me, everybody. Forgive me. Here, I'll do this real fast. See, and if you want to, go back and laugh, this is being recorded right now, so you can go back and listen to this, because this is worth listening to. So, all right. Okay. So, we started with this, and then we added this, right? A second sphere. Now we said that this sphere is a little bit different than the first sphere, right? In how? What way is it different? Right, go ahead.
It's hollow.
It's hollow, right? It has to fit around that first sphere, okay? And then we started adding a couple of different shapes, right? We started talking about these shapes. And we drew them, I kind of drew them as like a figure 8. I modified that to make them look sort of like this. So they're kind of figure 8-ish, all right? Real skinny in the middle, but wider on the outsides, okay? These are the next orbitals that show up, okay? Again, remember, this is all areas where electrons are likely to show up, all right? Not guaranteed, but probable, okay? And then we moved out a little bit more, and we added this, right? So we added blue stuff, okay? This is all the blue stuff that we added yesterday, right? The first blue thing that we added was this sphere, right? Then we added some more figure eights, right? But blue this time. And then, right at the end of class, we added a third shape, right? We added this kind of butterfly-looking shape, okay? That has these 4 lobes, sort of connected in the middle, but it has the 4 different areas, okay? Now, this is where it gets a little confusing. Ryan, go ahead.
Would everything in blue be considered one orbital?
No. Each one of those is a different orbital. We'll talk about why they're all blue here in just a second, okay? There is something that makes them similar, but they are not the same orbital. This, and this is the confusing part, this, notice here if I move it, this is all one orbital. It's all connected, okay? These are actually 2 orbitals. This is an orbital, and this is an orbital, okay? And then the easiest one to kind of tell which one is which is the sphere, right? And then that's one orbital. So I just showed you a total of 4 different orbitals. All blue, some different shapes, but they're all orbitals on their own, okay? Ronnie, go ahead. There are only 3 shapes. Well, there's actually 4 shapes, but I'm not going to show you the 4th one because it's too weird, okay? So we basically have the spheres, we have the figure eights, and then we have this one, which last year somebody said it looked like a butterfly. So I kind of go with butterfly on that one, okay? So those are basically the 3 shapes that you kind of need to identify. And then, Ronnie, it's just a matter of, okay, what color are they? And that's what we're going to get into a little bit more today, all right? Okay, go ahead. Okay, so remember, right? So here's all of that stuff put together, okay? Yellow in the middle, red next, then blue, okay? Remember that there's really kind of 2 things that these electrons are trying to satisfy. They're trying to get as close to the nucleus as they can because they're attracted to the nucleus, but then they're also trying to stay away from all the other electrons, at least as much as they can. Does that make sense? So that's why we start seeing these shapes, because you notice, right, with here, so like these red ones, right? Each one of these is an orbital, okay? But if you notice, they're oriented in a way to try and stay away from each other as much as possible, right? If you're on the x-axis, the farthest away you can get from the x-axis is the y-axis, right? And then, same thing is true, remember we said there was a 3rd one of these, right? The farthest you can get away from these 2 is to go on the z-axis. So it's that idea of, okay, we're trying to get as close to the can with the nucleus, but stay away from the other electrons. And that's why when you add this blue one, right, now we're trying to fit into those spaces as much as we can, okay? So really, it's just that combination of those 2 things, okay? So then, what we'll see, and I didn't have you guys draw this yesterday, and you don't need to draw this now, okay? But what we'll see is that this pattern then keeps repeating. So, right, now we've added a 4th color. I've added green, okay? Like I said, you don't have to draw this, right? This just gets too much, okay? But notice, right, green encompasses all the stuff in between, right? The first green thing that shows up is a sphere. The next green things that show up are the 2 figure eights. Then you got the butterfly, but they're all green, okay? Does that make sense, how we see that sort of pattern repeating itself? Okay, Lauren, go ahead.
Does the pattern just keep going?
Basically, yes. Although when we get to green, there is a 4th shape, but it's really 3-dimensional and really hard to draw in 2 dimensions. So that doesn't come up real often, Lauren, so we're just going to kind of forget about that for a second. We'll mention it in the outline, but there's no picture of it because you don't really start seeing those shapes until we start getting to like really big atoms, like, you know, like atoms that have 70 electrons, 80 electrons. And we're not going to go that high in our discussion because we're just trying to learn the basics for now. Okay? Does that make sense? All right, so let's talk about this. Yesterday, on the outline, if you flip it back to the front page of your actual outline, we talked about quantum numbers. And I gave you a definition for quantum numbers. What do quantum numbers do for us? Ryan, go ahead. Give me something else besides location. Okay? It's more of like an address, right? And when I say give me something else, right, it's not location, it's quote-unquote location, right? Because we don't know for sure. Just like an address. An address is a space, right? Your house has an address. That doesn't mean you're going to be there, but it still has the address. Each one of these orbitals that we drew yesterday, and the green ones that I added, have their own address. That address is called the quantum number, or the set of quantum numbers. Sorry, because I told Brian, how many quantum numbers does each orbital have? 4. All right, and with 4 quantum numbers, we can distinguish every single one of these orbitals from all the other orbitals. There will be some similarities between them, but at the end of the day, no orbital has exactly the same set of 4 numbers as any other orbital. Okay? Good there. All right. Let's start talking about these quantum numbers. So, the first quantum number is called the principal quantum number, right? Remember back from like, I don't know, 5th grade language arts, whatever, the difference between principal, P-A-L, and principal, P-L-E? Yes, no, maybe? What do your teachers teach you? Anyway, so principal, A-L, right, is like the main or the most important, right? It's an adjective, okay? But principal, P-L-E, is a noun. It's like an idea, okay? So the fact that this is the principal, P-A-L, quantum number tells you about the importance of this quantum number, all right? So by definition, first, we use the lowercase letter n to symbolize the principal quantum number. But it describes for us the main energy level where this electron is found. Electrons that have the same principal quantum number have similar amounts of energy. Not the same, similar. Okay? Meaning, if that's the case...
Good morning, everyone. Quick change of plans. Please follow the bells from this point. We were able to sit down quickly and reprogram our bells. Our bells should be accurate, provide full lunch periods.
Well, that doesn't mean we're leaving yet.
So follow the printed schedule, but the bells are now working. Thank you.
Oh, so are we following this printed schedule? Well, if we are, this period was supposed to end 2 minutes ago. So let's finish this up, okay? All right. So the principal quantum number deals with energy, meaning orbitals that are closer to the nucleus have lower principal energy or principal quantum numbers, and then those principal quantum numbers increase as we go farther and farther away from the nucleus. All right? Orbitals closer to the nucleus with lower principal quantum numbers have electrons with lower energy. Okay? Anybody want to make an educated guess as to how I represented principal quantum number on our elaborate drawing that we started yesterday? As we got farther and farther from the nucleus, what did I do? Well, that's N. Change colors. The colors on our drawing represent different principal energy levels that are represented by different principal quantum numbers. Okay? If we go back to our drawing, okay? So, here's the first color, right? Yellow sphere, it's all we got. All right? But then we added the reds, right? I drew you 3 reds, but technically there's 4, right? Because there's 1 on the z-axis, yes? Okay? These are farther out from the nucleus than the yellow one was. Electrons that show up in any of these orbitals will have higher energy than electrons in the yellow orbital. Okay? The next principal quantum number or principal energy level we added was the blue. There's lots of orbitals within that principal energy level because there's more space for them to spread out. All of these orbitals are the same principal energy level, and all of these orbitals would have the same, or energy similar. All right? We'll pick this up on Monday. I think I put a homework assignment on for the calendar for this weekend. Don't worry about it. I'll move it to Monday, all right?